Welcome to the MOOC on optical communications. Today we will be talking about the physical structure of optical modulator in this module. The plan for the module is that we will first review wave equation and then talk about wave propagation and then see what is the physical structure of a phase modulator and amplitude modulator or equivalently intensity modulator. So, let us begin by looking at propagation of an electromagnetic wave. We know that light is an electromagnetic wave. So, we would like to understand the propagation and the equation that governs the propagation of the light wave in a given medium. Okay. To do that, we need to invoke Maxwell's equations, because we picture electromagnetic wave or we picture light as an electromagnetic wave consisting of electric and magnetic fields. Okay. So, these electric and magnetic fields satisfy certain set of equations known as Maxwell's equations, and we will first very briefly recall Maxwell's equation, derive the wave equation, consider some very simple solutions of this wave equation known as plane waves, and then use this plane wave idea in order to study the physical structure of wave propagation inside a phase modulator and amplitude modulator, optical phase modulator and optical intensity modulator. So, let us first write down Maxwell's equations. As you probably remember, or you can take a look at any textbook, in an undergraduate electromagnetic textbook, you will discover that there are 4 Maxwell's equations which are given in terms of these 4 field quantities. Okay. The first equation, there is no order to Maxwell's equations. So, what we are writing is simply that is by convention, or that is something of my personal preference. So, we have what is called as Faraday's law, which in the differential form, this is called differential form of Maxwell's equation. So, you have curl of electric field E is equal to minus del B by del T. This del by del T stands for partial derivative of the magnetic flux density vector B with respect to time. Okay. So, E is the electric field, or sometimes called as electric field intensity, and this is measured in SI units in volt per meter. You have B, which is called as the flux density vector. This is the magnetic flux density vector, and this is measured in Weber per meter square or in Tesla. And then you have 2 more equations. H is called as magnetic field, or sometimes called as magnetic field intensity, and this is measured in ampere per meter in the SI units. And finally, you have flux density, which is now electric. Okay. This is measured in coulomb per meter square. So, these are the 4 field quantities which are functions of both space given by a general position vector r as well as time. So, these are all functions of both space as well as time. This position vector r will depend on which coordinate system you have chosen. So, in the Cartesian coordinate system, this will be given by, for any point which is described by the 3 coordinates x, y and z, this coordinate vector r is from the origin is given by x hat being the unit vector along the x direction, plus component along y and component along z. Okay. So, these are called as field quantities which vary both with respect to position as well as with respect to time. So, complete the Maxwell's equation now. So, you have this equation called as Faraday's law. Okay. Originally, Faraday's law was not in this form. What we are writing is the law in vector form. Okay. Next, we have Ampere-Maxwell law. Okay. So, this is Ampere was the original person who gave this law, but then this law was modified by Maxwell to introduce his famous displacement current. Okay. So, this gives you, this is given for curl of H, that is for the magnetic field, given by J, where J is the conduction current, plus del D by del T. This D is the electric flux density. So, the time rate of change of this electric flux density plus the conduction current will be equal to the curl of H. You have 2 divergence law. One law is del dot B equal to 0. Okay. There is one more law which relates del dot D equal to rho being the volume charge density. Maybe we can write this as rho v, so that this is volume charge density. Okay. These divergence laws are called as Gauss's law, one for magnetic fields and one for electric fields, right. If you consider a medium which is linear, homogeneous and isotropic, then this D field can be related to E field. Okay. D is given by epsilon 0, epsilon r into E, where epsilon 0 is the permittivity of the free space, epsilon r, which is greater than 1, is called as the relative permittivity of the medium. So, if you have a medium whose relative permittivity is epsilon r, then D is related to epsilon 0 epsilon r times E. So, if electric field line is arbitrarily directed in this particular direction, then the D field will also be directed along the same. Its amplitude will usually be quite small because epsilon 0 is a very small number. Okay. Similarly, B is related to the magnetic field H by this relationship. B is mu 0 mu r H, where mu r is called as the relative permeability of the medium. Okay. Again, you can see that both B and H have the same direction, but they will have different amplitudes. If the medium is anisotropic, as many optical elements are, okay, then D and E are related by a matrix. Okay. This D and E are related by a matrix, that is to say, in the rectangular coordinate system, the three components of the D vector dx, dy and dz is given by a matrix times the electric field vector E. So, you have epsilon xx, xy, xz. I hope you can fill up the rest of these elements here. This will be another 3 by 3, this will be a 3 by 3 matrix. Finally, you have the electric field components Ex, Ey and Ez. Clearly, you can see that isotropic medium is a very special case of anisotropic medium. In an anisotropic medium, all these elements are usually non-zero, which means that if electric field is directed along this direction, which I have taken arbitrarily, the flux density D will be directed. Okay, let us not make it perpendicular, although it is possible, let us keep it slightly general. So, this D field is usually directed at a angle with respect to electric field. Okay. So, this is something that is possible for a medium which is called as anisotropic medium. In an anisotropic medium, D and E are related by this matrix. So, many optical elements such as crystals are anisotropic in nature. However, not all these elements are filled for such a medium. It is possible to actually diagonalize this matrix. Okay. To diagonalize this matrix and to discover three new axes, which you can call them as capital X, capital Y and capital Z, which are not the same as X, Y and Z. These are two different axes. These are known as crystal axis. This is your reference frame. Okay. This is the frame of reference for X, Y, Z coordinates outside the crystal, but within the crystal there exist three very special directions which form the crystal axis. Okay. And this crystal axis is the result of diagonalizing this full matrix epsilon. Okay. So, if you diagonalize the matrix epsilon, you will discover three axes X, Y, Z, along which you will find that the D field will be in the same direction as electric field. Okay. So, let us make it little more specific. So, D capital X, D capital Y, D capital Z is the D field in the X, Y, Z or the crystal frame of reference. This is equal to some epsilon 0, which is the permittivity of the free space, times epsilon xx 0 0 0 epsilon yy. Please note that these are capitals 0 0 and epsilon z z. Okay. Times you have Ex, Ey and Ez. So, here you will find that D field and E field are directed in the same direction, but this axis X, Y, Z is usually not the same as the reference coordinates X, Y, Z of the frame that is outside of the crystal. Okay. There is a relationship between the two, but that relationship is not very important for us at this point. Okay. We are interested in looking at how the wave is generated and how the wave is propagating. Okay. But keep in mind that many crystals, and especially the one that is most widely used for making modulators, this is called as the lithium niobate crystal. This is the lithium niobate crystal. Okay. This is essentially anisotropic, which means that if my electric field is directed along x direction, it will see a different refractive index. If electric field is directed along y, it will see a different refractive index. So, this lithium niobate is an anisotropic crystal. Out of this anisotropic crystal, there exists one more special crystal. Okay. If this epsilon xx is equal to epsilon yy, but this is not equal to epsilon zz, okay, then such a medium is called as, or such a medium which is described by this particular scenario or situation is called as uniaxial materials. Okay. It is called as a uniaxial material or uniaxial crystal. Okay. This is about the material properties. Now, let us see how this Maxwell's equation imply that there is an electromagnetic wave and what is the equation that governs that one. Okay. To do that, let us assume that source of light or source of electromagnetic wave is located at very far away from the point where we are considering. So, let us say this is located at minus infinity and you are looking for fields or waves in this region, which is very far away from the region where you are considering. Okay. So, the region where you are looking for the waves is very far away from the region where these waves were originally generated. So, you can imagine a transmitting antenna with an antenna placed at minus infinity. Okay. As the antenna generates the electromagnetic wave, these electromagnetic waves will propagate through the medium. Okay. And because you are considering the region where there are no currents, right, there are no free currents in this region. I am considering free space, for example, or a medium of dielectric, there are no currents here, nor there is any charge, no one has sprinkled some charges. Okay. There are no charges sprinkled on any region that we are considering. So, both these quantities are equal to 0 everywhere in the region of wave propagation that we are interested in, J and rho v is equal to 0. So, what will happen to Maxwell's equation? Curl of H will be equal to del d by del t and curl of E will be equal to minus del b by del t. Del dot d will be equal to 0, del dot b was anyway equal to 0. Okay. These equations are known as source free Maxwell equations. These are known as source free Maxwell equation because the sources, namely current and free volume charge density, both are equal to 0. Okay. Now, what we do is we take the curl of this electric field curl expression. So, I take curl on both sides, obtain minus del by del t curl of b here. Okay. I have interchanged del by del t and curl operation. So, I can write this in this particular fashion. This left hand side can be expanded using a certain vector identity. Okay. I will not show you this vector identity or the proof of this expansion, you can find it in any good undergraduate electromagnetic textbooks. But for the right hand side, I realize that I am actually working with a medium which is simple in the sense that it is non-magnetic and having a relationship between B and H described by some mu. Mu will of course be equal to mu 0 and mu r, mu 0 into mu r. Okay. This I am calling this as mu because I do not want to write mu 0 mu r every time. So, with that I can, mu being a constant, can be taken out of this curl operation. In fact, it can be taken out of this del by del t term. So, you get minus mu del by del t. What is left here? Curl of H. But I know what is curl of H. Curl of H is given by this expression, which is del d by del t. But the right hand side can again be simplified when d is related to electric field. If d is related to electric field in this particular way, then epsilon being a constant, okay, I am assuming at this point an isotropic medium. Okay. For an isotropic medium, linear and homogeneous of course, epsilon is a constant, so it can be pulled out of this derivative. So, this can be written as epsilon del E by del T. Is that okay? So, this is how the right hand side would become. Now, you can, in place of del cross H, substitute this epsilon del E by del T. So, you will have epsilon del E by del T, pull epsilon out of this partial derivative. So, you get minus mu epsilon and whatever that is remaining is del square E by del t square. And we have seen that del dot D equal to 0 because there are no free charges in the region where we are considering wave propagation, but D is related to electric field. So, this gives you epsilon, or rather del dot epsilon E equal to 0. Pulling epsilon out of this equation gives me del dot E equal to 0. Okay. So, if you substitute this condition into this one, then this entire thing goes away, gradient of del dot E goes away, minus sign and minus sign will go away, and what you get is this equation which is called as the wave equation. Del square E is equal to mu epsilon del square E by del t square. You can further introduce the phase velocity of the wave by calling that Vp as 1 by square root mu epsilon. So, clearly mu epsilon will give you 1 by Vp square, where Vp is called as the phase velocity of the wave. So, this is equal to 1 by Vp square del square E by del t square. Okay. Instead of working with a general electric field, this left hand side is actually vector Laplacian, okay, which means that this del square operation must be applied to x, must be applied to the y component. So, you will have del square Ey plus you have del square Ez. So, this vector Laplacian must be applied everywhere to the 3 components that you have, and furthermore when you apply this del square, each of this del square is actually del square by del x square plus del square by del y square plus del square by del z square. Okay. So, this operator must be applied for Ex, must be applied for Ey and must be applied for Ez. When you do that, you will actually generate 3 separate sub wave equations, one wave equation for Ex, one for Ey, one for Ez, because the right hand side can also be split up in the same way. You have 1 by Vp square del square by del t square Ex, Ey and Ez. So, there are 3 individual x, y, z components for the electric field, to each of which you are taking this 1 by Vp square del square by del t square. Okay. So, what you essentially get is, say, del square Ex is equal to 1 by Vp square del square Ex by del t square. Is that okay? So, now you have, similarly you can write down one equation for Ey as well as one equation for Ez. In general, this equation implies that Ex must be a function of x, y, z as well as time. Okay. However, we will consider those waves which are called as uniform plane waves. Okay. In this uniform plane waves, what we have, so this must be written as uniform plane waves, what we have is the wave is propagating along plus z, or it can be propagating along minus z, but we will stick with wave propagation along plus z direction. Wave is propagating along plus z direction. In time, it varies as e to the power j omega t, or it varies as cos omega t. Okay. It is a sinusoidally varying wave. Its amplitude is varying sinusoidally with respect to time. Okay. So, if I assume these conditions, then this equation can be further simplified, because this operator del square by del t square becomes minus omega square. Okay. Because del by del t is j omega. So, if you multiply del by del t, or if you take del square by del t square, you get j omega times j omega, that is minus omega square. Okay. I can put that into this expression and also demand that this electric field be independent of x, it also be independent of y. Okay. So, the wave is characterized by propagation along z. In frequency, it has a certain frequency omega, and then it will be function only of z and time t. Okay. So, the wave is propagating along z, so its amplitude is expected to change as you go along z axis. Okay. Substituting all this, the equation can be further simplified. You will have d square Ex by dz square plus k square Ex equal to 0, where k square is nothing but omega square by Vp square. Okay. And this k is called as the propagation constant. So, this k is the propagation constant, or sometimes called as wave number as well. Okay. So, k square is omega square by Vp square. Actually, you will have minus omega square by Vp square in this expression. In this equation, you will have minus omega square by Vp square. I have pulled this term into the left hand side and called this as k square. This is a simple second order differential equation. Remember, we want a wave which is propagating. Therefore, the solution for this Ex as a function of z turns out to be some constant E0 and e to the power minus jkz. So that the total electric field, which is a function of z as well as time t, will be given by some constant E0 e to the power j omega t minus kz. Remember, I am writing this in the complex form, but in the real form this equation is nothing but E0 cos omega t minus kz. Okay. This is the equation that is propagating along plus z axis. It has a frequency omega, it has an amplitude E0. In fact, when we wrote down the expression for the field output or the light output from the laser diode, we wrote very similar to this, right. So, we said root Ps e to the power j omega st. We did not specifically specify that the wave is propagating along a certain axis. That was not important at that time, but here you can see that this is exactly equal to this wave which we are assuming. Okay. So far we have used the notion of uniform plane wave, but we have not told you that it was uniform plane wave. Why is it uniform? Because if you look at a constant plane z, so maybe you look at z equal to 0 plane. Okay. So in this z equal to 0 plane, okay, if you look at what is the direction of the electric field will be directed along x axis. So this from bottom to top, this is vertically up, arrows are the directions for the x axis, and no matter where you go along the x axis, you will see that the electric field vectors are directed always along x axis. Its amplitude may be at z equal to 0 something like E0, okay. At z equal to a different plane, z1 plane, the amplitude must be smaller because there will be a term kz, therefore the total phase for this one changes. So the amplitude might be smaller, okay, but it will be uniform. I am sorry, I have not drawn it nicely, but this should be uniform. Amplitude is small, but this amplitude is constant and is always directed along x axis. So this is my x axis, here also this is the x axis. You can find out what will be the corresponding expression for the magnetic field. You will find that the magnetic field must be y directed, so that the wave is propagating along z axis. Okay. Corresponding to this, the magnetic field must be y directed. I am not going to draw that one, but you can, I mean I am not going to derive that one, you can derive it for yourself. And if you plot what will be the magnetic field lines will also be constant and they will be directed along the y axis. Okay. They will be directed along y axis. Here again you can go along the x or y direction, the amplitude will not change. For a given constant z plane, the amplitude will not change. That is why this is called as a uniform plane wave. Okay. Why is it called plane wave? Because which is, if you look at this expression omega t minus kz, and if I set this one to certain value phi, okay, and ask for how does this phi look like, what is the plane for constant phi values. The plane for constant phi values are the planes of z itself, right. So if I say this phase must be equal to 0, which plane, how it would look at a time, say put t equal to 0, and then you find out where the phase will be equal to 0. So one solution is z equal to 0, correct. One plane that you will get, it will be z equal to 0, right. At t equal to 0, if I ask that the argument of this cos function will be cos kz and ask for constant phase points, and if I say phi is equal to 0 as the constant phase point, one plane that you will get will be the z equal to 0 plane, correct. So this plane will have, along this plane the phase will be constant. Which will be the other plane? Actually this plane would go like this, right. So this is the overall plane that is there. Maybe we can try writing a better picture for this. This is your x, y and z axis. So the constant plane that we were looking for is this z equal to 0 plane. So on this plane, for this wave, the phase will be equal to 0, right. Is this the only plane that we have? No, you will have one more plane at z equal to, when will this go to 0? Again when the argument goes to 2 pi, right. So at z equal to 2 pi by k, right. So at z equal to 0 and at z equal to 2 pi by k, you will have the constant phase, and if you look at this is actually a plane, the entire plane is rectangular in nature, right. There is no curvature to this, right. The planes or the points of constant phase will form a rectangle, or they will form a plane in this particular case. Therefore, this is called as uniform plane wave, and it is a wave because this is advancing along the z axis. Okay. The distance between two constant phase planes is called the wavelength of the wave, and therefore, you will see that wavelength is nothing but 2 pi by k, or k is equal to 2 pi by lambda. So, this was all about a wave which was propagating along a particular direction. Just to finish off this particular module, if the wave is propagating along x direction, then it is called as x polarized wave. If the wave is propagating along y, it is called as the y polarized wave. It is possible for you to have in general both x component as well as y component not equal to 0, and then the electric field E will be sum of two electric fields. One will be along x directed, that is x polarized wave, and one will be y polarized wave. Okay. Each of these waves, so let us call this as say Em is equal to some constant E0m e to the power j omega t minus k z. These waves are propagating along the same direction, but they might have different phases. So, phi m, where m is equal to x and y, that is to say Ex is equal to Eox e to the power j omega t minus kz plus phi x, Eoy e to the power j omega t minus kz plus phi y. Okay. Depending on the amplitudes Eox, Eoy, as well as the phase phi x and phi y, or rather the phase difference phi y minus phi x, which you can call it as delta, you will have different polarizations. Okay. The ratio of Eoy by Eox is given by an angle chi. So, described by tan of chi is equal to Eoy by Eox, and delta, if you define it as phi y minus phi x, then if tan chi is equal to 1, that is to say Eoy is equal to Eox, the amplitudes of x and y polarized waves are the same, but delta equal to minus pi by 2 or delta equal to pi by 2, you will get right circular polarized wave. Okay, this dot circle with a dot and r is circular for me, and this delta equal to pi by 2 will give you left circular polarized wave. Okay. You do not have to remember which direction the polarization is, but you have to remember that for a constant plane, so let us say z equal to 0 plane, if you look at how in terms of time the electric field vector, the tip of the electric field vector changes, it will change for a left circularly polarized wave, it will change like this, and for a right circularly polarized wave, it will change in this manner. Okay. The amplitudes will be equal, one will be anti-clockwise, the other one will be clockwise. I am sorry, I have kind of forgotten which one corresponds to which. Okay. This is largely a matter of convention. So, the way that I remember is if I take your right hand side and point it along the direction of propagation. So, this is direction of propagation. If you are curling from x to y in a clockwise direction, this is the right hand circularly polarized wave, and if you take a left hand thumb and if the thumb points in the direction of propagation and you are curling from y to x, this will correspond to the left circular polarized wave. Thank you.